Hi everyone, my name is Giacomo Barberi and I'm assistant professor at the University of Los Andes in Bogota, Colombia in the Department of Mechanical Engineering. Today I'm here to present a work that we did on thermographic indicators for the state assessment of rolling bearings. The presentation is going to be divided into an introduction in which we first introduce the problem that we faced in this work. Then we will present the experimental methodology, and then the thermographic indicators of rotating machinery that we identified in our work. And we will conclude with the resultant discussion and conclusion in future work. So concerning the introduction, we have that current maintenance strategies as progress from breakdown maintenance to preventive and then to predictive maintenance. Where in this context, predictive maintenance is defined as a condition-driven preventive maintenance program divided into three main activities: fault diagnosis assessment, prognostic assessment, and health management. So fault diagnosis assessment deals with fault detection, isolation, and identification. Furthermore, state assessment, we can also have inside the fault diagnosis assessment, state assessment, which is the activity for classifying the severity of failures or the health state of the physical asset in case the failure has not occurred yet. So we have here the curve, PF curve, in which we have the condition on the y-axis and the time on the x-axis, and we have that the condition go lower throughout the life cycle of our equipment. And the state assessment consists in identifying what is the health state of the equipment, in which here we have a failure, and here we have and here we have a failure, and here we have the initial of the failure. And so in case the failure has not occurred yet, consists in classifying the health state, so its position in the PF curve, or in case that we have a failure, identify the severity of the failure. So we can have several techniques that we can use for this, so like vibration, noise, etc. Here we will explore in this work infrared thermography, which is a non-contact and non-invasive tool that provides the temperature distribution of a measured surface as a thermal image. Infrared thermography has been used in different domains with like civil structures, electrical installation. However, it's used in rotating machinery has been much more limited. With the progressive decrease in the cost, in the price of infrared cameras and in the decrease in the resolution, become an attractive tool, so become interesting to study its usability for identify the state, health state of an equipment, so this for the state assessment problem of rotating machinery. So we can thermography can be divided into passive and active thermography. In passive thermography, the temperature of the object under investigation is recorded without an external heat stimulation, as the object itself acts as a source of heat. Whereas in active thermography, we have an external heat stimulation to be applied in order to take the data before the thermographic analysis. In rotating machinery, the defective regions appears as hotspots, and significant temperature difference exists between defect and defect-free regions. So that's the reason why we will study passive thermography. State assessment of rolling bearing is fundamental for improving the reliability and performance of rotating machinery, since bearing failures are among the most frequent causes of breakdowns. For instance, bearing faults account for the 44% of the total number of faults in the case of large induction motors. After a literature review, what we identified is just one work that was studying the use of infrared thermography for the state assessment of rolling bearings. Here, authors analyzed the spalling defect on the outer rates of rolling bearings, and through experiment, they demonstrated that the temperature on the bearing surface was proportional to the vibratory level generated by the progressive appearance of the defect. Therefore, infrared thermography seems viable for the state assessment of rolling bearing, even if the authors did not attempt to classify the severity of the failure. Therefore, motivated by the work of Misius and of this work, we decided to analyze different indicators for the state assessment of rolling bearing through passive thermography. So now we will explain the adoptive methodology, and in the next slide we will detail each phase. So we start with experimental setup, in which we use a transmission with an induction motor. We call this Unian's test bench, and this is a test bench that allows us to simulate bearing failure, shaft misalignment, and unbalanced loads. Moreover, different operative conditions can be run by changing the frequency supplied to the motor. So we can test different failures at different operative conditions, even if in this case we will just do experiment at one operative condition. And we also, in order to simulate different failures on the bearings, we generate different single point defect in the bearing outer race with electrical discharge machining. A notch was seated on each bearing for the definition of three severity levels. So we will experiment healthy bearing and three severity of failure. The factors that affect the accuracy of infrared measurement can be categorized as technical and environmental conditions. In the paper, you will find the details of this election. What I want to remark is like that we will use just one operative condition, since our idea in this paper is to identify indicators, and so we will study just one operative condition, whereas the study of the behavior of this indicator at different operative condition is left as future work. We then set, you can see a region of interest that is able to grab the behavior of the bearing, and then we take the temperature of the environmental temperature, since this is placed inside this this test bench is placed inside a laboratory, therefore is an indoor experiment, and in the indoor experiment we just need the environmental temperature. Then concerning the calibration, we did like an experiment in which we did a sort of duration test to identify the length of the test. And so we place the bearing of severity 3, so the most faulty bearing, and we make it run for 220 minutes. Then we plot like the maximum temperature over time, and we interpolate the behavior of the maximum temperature, and we identified this this exponential model, in which from this we were able to calculate the time constant of the temperature. So the time constant resulted in 43 minutes, more or less, and therefore we decided that having a test of 120 minutes would have reached the 93.7% of the temperature, therefore was an acceptable duration for the test. Eventually, we take a picture, like one picture each 2 minutes, that this corresponds to more than 20 times the system time constant, granting the acquisition of the transient behavior. Eventually, for the data collection, we converted thermal images in temperature profile matrix. In this way, we have real valued matrices to analyze in place of RGB images. So for the identification of the indicator, we look at the literature and we find some steady indicators for the steady state behavior. And so one quite used is the quantitative criterion, which is the relative temperature between the maximum temperature of the bearing, so the pixel with the maximum temperature, and the environmental temperature. Qualitative criterion, relative temperature between the maximum temperature of the bearing and the one of a healthy bearing operating under similar condition. And then we can have further indicators that can be identified by considering all the pixels of the region of interest, and not only the maximum temperature as were the quantitative and qualitative one. So these are like the mean, the standard deviation, and for example, the percentage of pixel above a certain threshold. Then we also identify some indicator for the transient behavior. And in this case, we identify a first order differential equation that represents the behavior of the temperature behavior of the bearings. And by solving this first order differential equation, we can identify an exponential model that represents the behavior of the bearings. This model, we can identify two constants, K1 and K2, and these two will be utilized as indicators. So in summary, let's say we have identified all these indicators. Some the first 6 are relative to the steady state behavior, and the last two to the transient behavior. To identify the potential of one of these to be like an indicator for the state assessment, we identify a monotonic tendency criterion. So we expect a monotonic tendency with the state default condition of the bearing. And we can notice that 4 out of 8 indicators presenting a monotonic tendency, so showing a potential in, let's say, in identifying the state assessment of the bearing. However, we may have possible outliers since we repeat the experiment just once. However, let's say the objective of this work was just to identify, let's say, potential indicators while their validation is going to be left as future work. So, as summary, we explored the use of infrared thermography for the state assessment of rolling bearing. We identified some potential indicators relative both to the transient and steady state behavior. And this indicator came from the domain knowledge, which in other domains, it was demonstrated that indicators from domain knowledge always are at potential for the state assessment of state assessment problem. Future, we would like to repeat the experiment to validate these indicators. We would like also to validate these indicators at different operative conditions, as we did just these just for 60 Hz. And finally, we would like also to evaluate the robustness of this indicator to different noise conditions that can be typical of industrial workplaces, such as dust or light. So thank you very much, and I'm open to any questions and suggestions. Bye.